Okay, so we had a test on Friday, and my plan is to have the statics. What? Another one? We had. Oh. Um, so my plan is to have the statics tests graded and back to you on Wednesday, and then the thermo tests graded and back to you this Friday. Um, okay, and we've started to talk about relationships between different properties in a single state, how you can figure out, how you can calculate properties based on knowing other property values. Um, so we're talking about equations of state. And that is if you know some properties, how can you determine other properties? Um, and the first answer we talked about to this question is tables and websites. But then another approach to it is to use simplified material models. And so that's what we're talking about right now. And the two that we're going to talk about are incompressible materials. For us, that's liquids. You can sometimes use this with solids, but like I've said before, solids just aren't very important to us as engineers. The thermodynamic properties of solids, I mean. And then the other simplified material model that we're going to use is ideal gases. Um, so this is what we're talking about right now. And we started with this new definition, this new property, enthalpy, that is capital H, and it's just equal to the internal energy plus the pressure times the volume. And we're often going to use specific enthalpy. That's a lowercase h, and you can get that by just dividing the total enthalpy, the true enthalpy, by the mass of material you have, or you can also calculate it as the specific internal energy plus the pressure times the specific volume. And then once we had that definition, we could define specific heats. And they have a complicated mathematical definition, but in some cases, this complicated definition simplifies to something easier to use. So the specific heats, we had two of them. The first one was the constant volume specific heat, CV, and that is the partial derivative of the specific internal energy with respect to temperature, calculated with a constant volume. And then the second one is for it's the constant pressure specific heat, C sub P, and that is the partial derivative of the specific enthalpy with respect to temperature calculated at a constant pressure. So that's just a reminder of where we are. And so now I'm going to talk about incompressible materials first. You can think of the definition of an incompressible material as constant density. So no matter how much pressure you put on an incompressible material, a certain amount of volume is going to have the same mass. You can't squeeze more mass in. Like marshmallows don't have constant density. You know what I mean? Like if you put a lot of pressure on a bag of marshmallows, you can squeeze it down into a tiny area, and it has a lot more mass a tiny volume, and it has a lot more mass per volume, But water doesn't do that. You can't squeeze a lot of water into this much, no matter how much pressure you apply. Okay? Liquid water. Steam does do that, but not liquid water. Okay? So constant density is like the definition of incompressible. And that also, since specific volume is the reciprocal of density, that also means constant specific volume. And we're going to use this for liquids. And here are the things that we can use for incompressible materials. So first of all, because it's kind of part of the definition of incompressible materials, we can say that the specific volume is constant. Second, this is a super important one. The specific internal energy for an incompressible material is only a function of the temperature. One thing that means is, one consequence if you want the specific internal energy of a liquid, you can use the saturation tables at your desired temperature. And then the last thing that's going to be useful for us, so there's only really 3 of these that we're going to use over and over again, is that these 2 complicated specific heats, the constant volume specific heat and the constant pressure specific heat, are equal to each other, and they're both just equal to du dt. And one nice thing about liquids is that, so not only is this true, and we're just going to call this C, by the way. since they're both the same. That's only true when we're talking about liquids. Um, when we're talking about gases, we have to keep those two things separate. But with liquids, we're just going to call it C since they're the same. But also, another nice thing is C doesn't change very much as the temperature changes. Okay, so you can pretty much look it up for the temperature range you're interested in. I'll call it your temperature range. And then once you've done that, you can treat it as constant for the math. Um, so the first thing I want to say is, I want to just point out why these are true for incompressible materials. Why are CV and CP equal to each other and equal to just the total derivative of the specific internal energy with respect to temperature? So first, let's think about CV. And we'll start with the definition. So that's equal to the partial derivative of U with respect to temperature for a constant volume. Well, there's two things that you notice. The first one is for an incompressible material, volume is always constant. And then second, since the specific internal energy is only a function of temperature, so you only need that partial derivative definition if things are functions of multiple variables. That's what a partial derivative is. Okay. So du dt, or partial of u with respect to t, is just equal to du dt. Okay. So that one's pretty easy to see, just based on our assumption, our treating the specific internal energy as a function of temperature alone. So now why, for the constant pressure version, why is it true? Well, Cp is defined as the partial derivative of the specific enthalpy with respect to temperature at a constant pressure. This one doesn't just instantly, we don't know that the pressure is always constant for an incompressible material. That's not a definition of incompressible material. Pressures can change. But let's break up specific enthalpy into its definition. So C sub P is equal to the partial derivative with respect to temperature of the definition of specific enthalpy, remember, is specific internal energy plus PV. And we're still doing this for a constant pressure. And now we'll think about these separate terms. This is only a function. I thought we were going to get welcome to Rydell High. Is that what it's called in Greece? Rydell? Isn't that what they do? No one's seen Greece. That's like before your grandparents were born. Okay, so specific internal energy is a function of temperature. So that first term just becomes, we can think of this as, if I simplify this now, we can think of this as du dt plus partial dt of PV at constant pressure. And now let's look at that second term. Well, V is always constant because it's incompressible. P is constant because we're doing this at constant pressure. And so that whole second term goes away. And so Cp is just equal to the total derivative du dt, and we're going to call that C also. So why did I make you sit through this? I just want you to notice you don't have to remember these derivations. Just remember that you can reason out without crazy math or anything why CV is equal to CP, and we just call it a single thing, and it's equal to the total derivative of U with respect to temperature. Okay. Okay, well, let's do an example of how this is useful. So let's say we have 2 kilograms of liquid water. And let's say it's going, there's a process where it goes from 320 degrees Kelvin to 324 degrees Kelvin. As the pressure goes from 1.01 times 10 to the 5th pascals to 1.40 times 10 to the 5th pascals. And for this range of temperatures, well, I'll write that in a second. But here's what we want to do. We want to calculate the change in extensive internal energy. And second, we want to calculate the change in extensive enthalpy. Well, we're going to do this with the incompressible material assumption, and then we'll go to the website uh, and compare the answers. Okay, see how close it is. Okay, so if we assume that a material is incompressible, then there's a value for C at a given temperature that we can look up. And we look up C for this temperature range. And we get that C is equal to, it usually gives it in kilojoules per kilogram Kelvin. So it would be like, it would say 4.18 kilojoules per kilogram Kelvin. And you have to remember, if we're doing these in SI units, to convert that to 4180 joules per kilogram Kelvin. And so now we can say that 4180, which is C, we can use the definition of C. This is equal to du d temperature. Okay, we can think of that as the definition of C for an incompressible material. And now we can integrate both sides. So I like to think of this as multiplying both sides by dt. So we can write this as 4180 dt is equal to du. And then we can integrate both sides. So we're going to integrate from state 1 to state 2 in both cases. If you integrate the left side, you get 4180 T. And we're going to evaluate from state 1 to state 2. So what's the temperature at state 1? Oh, yeah, 320. But right. 320. And then the state 2 is 324. And then if we integrate this one, we get U evaluated from, I'm just going to write this as U1 to U2. Do these evaluations and you get 4180 times the quantity 324 minus 320 is equal to U2 minus U1. Well, the definition of U2 minus U1 is the change in specific internal energy. Notice we're trying to calculate that change in extensive internal energy, so that's sort of the form we want. And so do that multiplication, and you get that delta U, delta little u, is equal to 16.72 times 10 to the third joules per kilogram. Now we want the change in extensive internal energy. So delta big U is equal to the mass times the change in delta little u. I said there was 2 kilograms of this, so we have 2 times 16.72 times 10 to the third, and we get 33.44 times 10 to the third joules. So that was part A. And now we want to calculate the change in the extensive enthalpy. So how are we going to do this? So yeah, just think through what we know. What relationships do we know that could help us here? Well, we know that the change in specific enthalpy is equal to the change in specific internal energy plus the change in pressure times specific volume. We just calculated the change in specific internal energy. So that's 33.44 times 10 to the third. And then plus, so now the change in pressure times volume, how are we going to calculate that? Well, what do we know about the specific volume for an incompressible material? It doesn't change, so we're just going to use one value for that. We know the change in the pressure, so we can just think of this as specific volume times the later pressure minus the earlier pressure. Now we can look up this specific volume for our temperature range, in a table or whatever. So for our temperature range, what's the density of water at sort of standardish atmospheric pressure and room temperature? The density? Yep.
1 kilogram per liter.
Let's see. Okay, I think of it as 1,000 kilograms per cubic meter, or 1 gram per cubic centimeter. I assume that's the same thing, but I can't do it in my head. So this is 1,000 kilograms per cubic meter. And so that means that the specific volume is 0.001, just the reciprocal of that. And so delta H, little h, is 33.44 times 10 to the third plus 0.001 times 1.4 times 10 to the fifth minus 1.01 times 10 to the fifth. And, whoops. I use the extensive volume here instead of extensive internal energy instead of the specific. So this should have been 16.72. This should be 16.72.
Professor?
Yeah.
Is the starting pressure 1.01 E3 or 1.0?
I think it said E5. Did I write it as E3? E5. Yeah. Okay, so do this and it comes out to 55.72 times 10 to the third joules per kilogram. We want the change in the extensive enthalpy. So this is equal to the mass times the change in the specific enthalpy. So this is 2 times 55.72 times 10 to the third. And so that is 111.44 times 10 to the third joules. Okay, this is a simplified model. We're assuming that there's no change in density or change in specific volume as this process takes place. That's not exactly true, but it's very close to true. And so let's look it up on the website and see what it says about these values. Okay. So this is an approximation using the simplified incompressible model. So let's compare it to the table or the website. So I'm going to go, so first I'm going to go, so we're talking about liquid water. At state 1, we have a pressure of 1.01 times 10 to the fifth and a temperature of 320 Kelvin. And we're going to look up the specific internal energy, and we're going to look up the specific enthalpy. And then we're going to do the same thing at state 2 for a pressure of 1.4 times 10 to the fifth and a temperature of 324 Kelvin. We're going to look these up. And then we'll subtract and see how close our approximation was. Okay, so I'm going to do this for water. And I'm going to use SI units. My starting temperature is going to be, this is in Celsius, so 320 minus 273.15 is 46.85 Celsius. And then pressure, this is in kilopascals, so 101. And we'll calculate those properties. And it says that the specific internal energy, where is that? Internal energy is 196.1 times 10 to the third. This is in SI units. And the specific enthalpy is 196.2 times 10 to the third. And now I'm going to do the same thing for state 2. So now we're talking about 4 more degrees, so 50.85, and an absolute pressure of 140. And we have a specific internal energy of 212.9 times 10 to the third. A specific enthalpy of 213.0 times 10 to the third. And so the change in internal energy is 212.9 times 10 to the third minus 196.1 times 10 to the third. And that is 16.8 times 10 to the third joules. So how close were we? Very close. And really probably we're closer than even that says. They're just using fewer significant figures than we are. And then for the change in specific enthalpy, so we got 213.0 times 10 to the third minus 196.2 times 10 to the third. And that should, well, that should come out the same, right? 16.8 times 10 to the third joules. How does that compare to our value? Not very close. That was not what I was hoping to see here.
They use the, not the specific range of energy, internal energy.
Oh, okay.
Like,
yeah, okay. Thank you. Okay, good.
Your calculations on the actual
Okay, so I should have put in, where is it? So I should have put in 55.72.
I think when you like actually calculate that, you just
0.1, 55.72. So 50.85 Celsius, 140 kilopascals. Calculate these things. Let me just look at this for a second and see if I did. So in my calculation,
we just like that card the second one with delta
This one? Okay, so the change in specific internal energy I did right. So 16.72 times 10 to the third plus 0.001 times okay, and this time I got so yeah, that calculation just wasn't right here. This should come out to be 16,759. And this one should come out to be 33,518. And now this is within the, within the precision of the significant figures that they're using on the website. Okay, so the take-home message here is this incompressible simplification gives very accurate results. And these results are more accurate as the range of temperatures goes down in the process, or more accurate for smaller temperature ranges. And you might have used slightly different notations or whatever, but this is very close to anybody who took, who did some thermodynamics in Physics 1. This is very close to probably what you did for calculating changes in internal energy in a material based on a temperature change. Okay, you probably didn't talk about the more complicated definitions of these specific heats. You just jumped right into thinking of there being one single specific heat and using that to calculate relationships between changes in internal energy and changes in temperature. Okay, but this lets you do that. So next time we're going to talk about ideal gases. I'm not going to get into this yet, but so next time we'll get into the ideal gas approximation. And, we'll see what kind of similar things we can do for ideal gases. Any questions? I have a couple of problems I can give you on using this incompressible assumption. Okay, that's all.